Language is inherently ambiguous. Words take on different meanings depending on the surrounding text. This property, known as polysemy, represented a technical barrier for early natural language processing models. Models like Word2Vec and Glove used a dictionary-style approach to map language. They assigned every word type a single fixed set of mathematical coordinates. This approach relies on a strict architectural assumption. The vector for a word is constant across all occurrences. This diagram shows a static lookup matrix. If we input the phrase "play the game," the model maps "play" to a specific cell. If we input "play the theater," it traces to the exact same cell and outputs identical mathematical vectors. Since the assigned vector is context independent, the model cannot distinguish between a sport and a stage production. Polysemy remains invisible to the architecture. Treating language as a static lookup table created a hard ceiling for artificial intelligence, limiting its capacity for nuanced reading comprehension. In 2018, researchers from the Allen Institute and the University of Washington published the ELMo paper, introducing a method for deep contextualization. ELMo replaces the static matrix with a dynamic mathematical function. The word vector becomes a calculation based on the entire sentence and the specific position of the word within it. The system achieves this by extracting the internal states of a pre-trained bidirectional language model as it processes text. The architecture defines a word vector as a sentence-dependent calculation. This shifted the technology away from simple table lookups toward dynamic feature generation. To see how this function is actually computed, we can trace the data flow of a single token as it moves through the ELMo architecture. The foundation is a character-level convolutional neural network. Raw text characters feed into this CNN block, outputting a base token vector labeled XK. This static floor is context-independent. It remains the same regardless of the surrounding words. Processing characters instead of whole words allows the model to handle out-of-vocabulary terms by assembling their vectors from recognized subword parts. Before analyzing the broader sentence-level context, the model securely grounds itself by representing the raw morphological shape of the word. We build the Contextual engine using two stacked LSTMs. The forward pass moves left to right, predicting tokens based on past words. Simultaneously, the backward pass moves right to left, evaluating future context. At position K, both outputs are concatenated into a single block. Because the forward pass evaluates the past and the backward pass evaluates the future, the resulting vector is conditioned on the entire sentence by structural necessity. For every token, the architecture produces two L+1 representations, the base token layer plus the forward and backward outputs for every LSTM layer. This presents an engineering choice. With a full stack of vectors available, a developer must decide which depth contains the most relevant data. Conventional wisdom often favored the top layer. Probing studies clarified the layer's roles. Parts of speech tagging, a syntactic task, achieves its highest accuracy at the lowest by LSTM layer. Word sense disambiguation, requiring semantic understanding, peaks at the top layer. Bottom layers focus on syntax, top layers encode semantics. Relying solely on the top layer discards important syntactic information. True linguistic comprehension requires signals from every depth of the network. This finding led to equation 1, the deep mix. All layer outputs route to a final summation node. The ELMo vector is calculated using parameters Sj, which are weights learned for each layer, then scaled by a global factor, gamma. This task-adaptive approach automatically learns to favor lower layers for syntax and upper layers for semantics. Furthermore, if weights favor only the base layer, the LSTM outputs zero out, perfectly collapsing the equation back into the static token vector, xk. This mathematical elegance allows ELMo to function as a standard lookup or expand into a multi-layered contextual representation depending on the needs of the task. To use this in practice, the massive biLM is frozen. The token vector and the ELMo vector are concatenated and fed into a downstream task model. During training, developers use dropout and lambda regularization, stabilizing the process by biasing learned weights toward the layer average. This chart shows the empirical impact. ELMo produced a 6 to 20% relative error reduction across 6 major language benchmarks, setting new state-of-the-art scores. The system achieved these gains using only monolingual text for pre-training, removing the need for the expensive parallel datasets used by previous models. ELMo demonstrated that a single frozen contextual engine could serve diverse language tasks through a lightweight mathematical combination. The architecture had specific limitations. The use of LSTMs made inference computationally slow, and the bidirectionality was relatively shallow, lacking the deep cross-attention found in later models. ELMo's raw language modeling score was 39.7, which was less efficient than the forward-only state-of-the-art at the time. This highlighted a key lesson. Downstream task performance can be decoupled from the raw generation quality of the language model. ELMo's primary value was its ability to produce rich, transferable features for other models. This evolutionary timeline shows the model's legacy. Later that year, BERT adopted ELMo's contextual pre-training approach, but replaced the LSTMs with deep bidirectional attention. ELMo broke the assumption that a word type is a single vector. By replacing the static lookup matrix with a sentence-dependent function, it transitions the field into the contextual era.